Okay, gentlemen, so today we're going to talk about the 5 different types of reactions. And in addition to that, we're going to talk about how to predict products based on those reactions and how to balance equations and do all that stuff we should have known how to do already for a while. So that's what we're going to do today. I'm going to go over a board presentation I made, a smartboard presentation. So you'll see that on the screen as I talk over it. And then I'll come back a couple times to indicate other things. Okay, gentlemen. So today, again, we're talking about the types of reactions, and there are 5 general types of reactions that you should be learning. We got combination, also known as synthesis, decomposition, single replacement, double replacement, and combustion. For single replacement and double replacement, you may also see them called single and double displacement. They're synonyms. More commonly, books are using replacement now, so that's what I'll use. But if you see displacement somewhere on a worksheet or something, it's just the same thing as replacement. I'm going to go through these one by one and talk about what is going to happen for each with what they start with and what they make. So each one starts with something unique and has a very specific process and makes something predictable. So we are going to start with combination or synthesis. It's very simple to recognize if you have the whole equation. Whenever you start with a bunch of reactants and they make one product, that is synthesis. So 2 or more reactants combine to make one product. So here I have water being made, so hydrogen and oxygen combine to produce water. You got two reactants, one product. That would be synthesis. And just remember for things like H2 and O2, the Brinkelhoff things, they're always doubled. So it's H2 and O2, which affects the balancing. What I would expect you to be able to do, if I give you the whole equation, just recognize it as combination. So even if it's more complex, as long as a bunch of things combining into one product, that's combination. If I only gave you the first half, so I only gave you, as in the product prediction example, aluminum and chlorine, I would expect you to combine them into an ionic compound. So the only prediction I will expect you to do is metal plus nonmetal makes ionic compound. And we've actually done these before. When we talked about ionic compounds, we talked about what happens when this metal and this nonmetal combine. Now we're just talking about it within the context of a full chemical reaction. So when a metal and a nonmetal combine, the metal gives up electrons to the nonmetal. They become a positive cation and a negative anion. We've done that before. So with aluminum and chlorine, if I started out with just said aluminum and chlorine, first of all, again, chlorine is one of the Brinkelhoff doubles, so just make sure you write that. Aluminum and chlorine are going to combine, and they're going to combine into aluminum chloride, and they're going to combine in such a way that their charges cancel out. So you have to balance the product charges, the charges in the product, this +3 on aluminum and this -1 on the chlorine. Again, that determines how they combine. So aluminum, because of where it is on the periodic table, is +3. Chlorine is -1. So you need 3 -1s, 3 chlorides, to balance out the aluminum. So aluminum chloride is AlCl3. And because of that, then once you have that product, you can balance the whole equation with 2 aluminums and 6 chlorines on both sides. So it's 2 aluminum plus 3 chlorines, 3 Cl2s, gives you aluminum chloride. Again, two reactants make one product. That is combination or synthesis. Okay, gentlemen, so the second type of reaction that we're going to talk about is decomposition. And decomposition is one of the easiest ones to recognize because you start with just one reactant. So if you see one thing and then an arrow, that's got to be decomposition. All it can do is break down. So one reactant breaks down into 2 or more simpler products. In our example, we have mercury 2 oxide breaking down into mercury plus oxygen. Again, with oxygen, notice it, right? I wrote Brinkelhoff above it. It's O2, which affects the balancing. Just be careful with those. You should know all those. And just remember, if you have any of those elements alone, those Brinkelhoff elements, they're something too. Generally, these require something like heat or UV light or electricity because you have to break those chemical bonds. So in the case of mercury oxide, it requires heat to separate the mercury from the oxygen. Water which I use down below as an example, you can use electricity to separate the hydrogen from the oxygen. You can also do that with sodium chloride to separate into chlorine gas and sodium metal, though you need a lot more electricity for that. So if I give you the whole equation and you see one reactant and then a bunch of products, that's going to be decomposition. You will not have to predict like complicated products or anything. So if I expect you to do product prediction, I would give you a binary compound. That just means something made out of two elements, like, again, mercury oxide or water. And when you break it down, when you predict the products, it just breaks down into the two elements. So things can break down more complexly than that. They can be like really big compounds that break down into smaller compounds or maybe some elements. We're not going to be predicting that. You'll be asked to predict something like these two examples, where like I give you mercury oxide or water, and you separate them into their elements, mercury and oxygen or hydrogen and oxygen. Again, down here with hydrogen and oxygen, just remember, these guys are Brinkelhoff, so that affects that they're H2 and O2. And then after you predict the products, you can balance the equations. For some of the worksheet and on the quiz, I might ask you to balance some of the equations. If I don't specifically ask for it, you don't have to do it. But just be aware, you may still be required to balance some equations. So that is decomposition, the splitting apart of a chemical compound into simpler pieces. Okay, so the next two reactions are single replacement and double replacement reactions, and they're a little more complicated. So I'm going to start with single replacement. Single replacement always starts with an element by itself plus an ionic compound. So an element by itself plus a compound made out of a metal and a nonmetal, or a metal and a polyatomic ion. The only exception to that is it could be hydrogen plus a nonmetal. So something like HCl. Acids act kind of weird and sometimes act like ionic compounds. It can even be water. But a metal by itself plus a compound is pretty much always going to be single replacement for our purposes. And what happens is the metal by itself, or the element by itself, it can be a metal or a nonmetal, with the ionic compound, is actually kind of desperate. It wants to be in a compound. Things want to be in compounds. That's why they react to make compounds. In this case, we have calcium right here, and calcium would like to give up some electrons and be in a compound, and it needs something to take its electrons. And over here we have this lead-4 oxide, and the lead-4 oxide is happy, but the calcium would rather be with the oxygen. So calcium wants to be with oxygen, it's positive, oxygen's negative. Lead wants to be with oxygen. So there are rules that determine which one gets to be with oxygen, basically which one is more attractive. And these rules are called an activity series. Basically, it shows which metals and nonmetals are stronger than other ones. The stronger you are, the more you get to kick another metal off a compound. In our case, calcium is higher on the activity series. It's more attractive than lead. So the calcium is actually going to kick that lead off and end up with the oxygen, and the lead is going to have to go cry in the corner. I have an activity series on the next page here, apparently all the way down here. And as you can see, calcium here is much higher than lead. The rule is any metal or non-metal, depending on what series you're looking at, can replace anything beneath it. So lithium can replace everything. It's the strongest and most attractive. And silver is kind of sad and pathetic and can't replace anything. So that's how that rule works. If you get something where the element by itself is lower, then you end up with no reaction. Nothing happens because the element that's lower can't replace a higher element. It's not as attractive. So going back to our calcium and lead, the calcium can replace lead. It'll end up with the oxygen. So here's the calcium replacing the lead, ending up with the oxygen. And when you make the products, again, you have to balance charges. You're going to be making an ionic compound, which means something that's a metal that's positive and something that's a non-metal that's negative. Calcium is +2 because of where it is on the periodic table, and oxygen's -2. So you just end up with one Ca and one O, one calcium and one oxygen, +2 and -2, they cancel out, plus lead by itself. When metals or non-metals are by themselves, you don't have to worry about their charges. But for the non-metals, if I go to the list and you look at the non-metals, you'll notice that they are Brinkelhoff nonmetals, so fluorine, chlorine, bromine, and iodine. So they are, if they're by themselves, F2, Cl2, Br2, and I2. So in single replacement, the element by itself tries to replace one of the elements on the compound. If it's a metal, it tries to replace the metal part. If it's a non-metal, it would try to replace the non-metal part. If it's higher on the activity series, if it's more attractive, it can do that, and the reaction happens. The other metal gets kicked off the compound. The metal that was by itself, or non-metal that was by itself, gets to be in the compound and be happy. And you balance the charges, and then you can balance the whole equation. So I balanced the charges first, this CaO plus 2 minus 2, and then I balanced the whole equation, 2 calciums plus 1 lead-4 oxide. It gives us 2 calcium oxides plus 1 lead, 2 calciums, 2 oxygens, and 1 lead on each side. Again, it is important that calcium is higher than lead on the activity series. That's what allows it to replace lead. Calcium is more attractive than lead to the oxygen. So that's single replacement reactions, and you should be able to determine whether something is going to make a replacement. You have the activity series, both that list. It's both on this page right here, and I will put this up in lectures. This as my notes as a PDF. And it's also on the PowerPoint that goes with this, PowerPoint 11.2. In fact, it's this exact one that I took from PowerPoint 11.2. So that is single replacement reactions. You should be able to identify them and predict the products and balance the equations. Okay, gentlemen, we're getting there. Got 2 types of reactions left, and one of them, double replacement, is actually not too bad. It's relatively easy. Single replacement, I think, is the most difficult. Double replacement, you always start with 2 ionic compounds. So a metal and a non-metal, or a metal and a polyatomic ion. By the way, just so you know, in this PowerPoint, or sorry, this board notes I've put up, and I'll put them up on a PDF under notes, I have included a polyatomic ion sheet as well as a periodic table. So you can reference those just in here, or, you know, you can use your own you have and have kept safe and sound and, you know, looked at lovingly every night at home. So in this case, in my example, we're starting with barium hydroxide and sodium sulfate. And whenever you start with 2 ionic compounds, as long as you can identify those as ionic compounds, we've got a metal barium and a polyatomic ion hydroxide, and a metal sodium and a polyatomic ion sulfate. That means they're going to be it's going to be a double replacement reaction. And what happens is pretty simple. There's a positive and negative part for each of these, a cation and an anion. They switch partners. I like to think of it as the cation switching partners. You can think of it as the anion switching partners. It really doesn't matter, because either way, you get the same thing. They switch partners. The barium is going to go, so the barium here is going to go with the sulfate, and the sodium here is going to end up with the hydroxide. So you'll end up with barium sulfate and sodium hydroxide. So the cation switch partners, I wrote that out over here, barium with sulfate and sodium with hydroxide. Now, when you do this, you're making ionic compounds, which means you have to check the charges and balance them. Barium is +2. Sulfate, if you look it up, is -2. Barium, just to be clear, barium is +2 because it is in the second column of the periodic table. Remember, for the periodic table, this first column's all +1, second column's all +2, then we skip the D group. Boron and aluminum are +3. Carbon does nothing, carbon and down. The nitrogen and down, that column is -3. Oxygen and down is -2. The halogens, fluorine, chlorine, bromine, etc., are all -1, and the noble gases don't do anything. So barium, being in the second column, number 56 here, that's +2. And sulfate, if we were to look it up, it's the bottom one in the middle here, it's -2. So they cancel out. Barium and sulfate cancel out. Same thing with sodium and hydroxide. So if we look at sodium, first column +1, hydroxide is listed right here, it's -1. So we check that, excuse me, went too far there, and we just have 1 barium and 1 sulfate because they're +2 and -2, and 1 sodium and 1 hydroxide because they're +1 and -1, so you don't have to do anything with that. They're all set. Then you can balance the entire equation. I put this yellow 2 coefficient in here because we needed 2 sodiums and 2 hydroxides on each side. So you balance the charges first, make all your products, and then you balance the whole equation. But double replacement, 2 ionic compounds, and the cations switch partners. So the cation with the one goes with the anion from the other one, and vice versa, and that is a double replacement. Okay, gentlemen, last one. If you made it this far, congratulations. You managed to stick through all of like 20 minutes of a lecture. So good job, good attention span. So last one is combustion, and combustion is anything reacting with O2. If oxygen gas is one of the reactants, O2 is one of the reactants, that's combustion. Generally, this means fire. So it's what you think of. It doesn't have to be fire. If it's going slow, it can be just a little bit of heat, but generally this means fire. There are 2 types that you're going to have to know about. Combustion of an individual element, and this is the same thing as synthesis. So when you have an element combusting, it can also be synthesis. So I use the same example I did for synthesis. If you go back and look at synthesis, I actually use this example. Hydrogen plus oxygen, well, it's combining with oxygen, so it's combustion. And hydrogen plus oxygen make water. If it's a combustion of a metal, it'll make an ionic compound, metal plus oxygen. If it's a non-metal that you're combusting, it'll make a molecular compound, 2 non-metals. So in this case, hydrogen plus oxygen gives us water. That's combustion, and it does create quite a bit of fire. If I have time, I believe in a week or 2, we'll get to limiting reactants, and we'll actually see some nice hydrogen-oxygen making water type explosions. I'll video it if we aren't in class by then. So the second type is combustion of a hydrocarbon. A hydrocarbon is something shockingly made out of hydrogen and carbon. It can also have oxygen. So I usually write it out like this, where X just stands for any number. So CX, HX, it has to have carbon and hydrogen, and it can have oxygen. If it doesn't have oxygen, it works the same way. If it has oxygen, it works the same way. No matter what, if you combust a hydrocarbon, so hydrocarbon plus O2, you're going to get carbon dioxide and water. Those are always your products. Those are the only products, CO2 plus H2O. So the easiest one to predict. You see hydrocarbon and oxygen, it's just CO2 and H2O. And then you balance it. You don't have to worry about balancing charges on CO2 or H2O. It's CO2, carbon dioxide, and water every time. So this is CH4 is methane, the burning of like the Bunsen burner or natural gas. So CH4 plus O2, well, CH4 is made of carbon and hydrogen. It's a hydrocarbon. It's combusting, reacting with O2, so you get carbon dioxide and water. And it wouldn't matter if it was, say, octane, C8H18, which is what gasoline is primarily of. If that's another hydrocarbon reacting with oxygen, you get CO2 and H2O. Every time you combust a hydrocarbon, you get CO2 and H2O. You just get different amounts of CO2 and H2O, depending on what you're combusting. In this case, we get 1 carbon dioxide and 2 waters to balance it. So that is combustion, and that is the last of the 5 types of reactions that you have to do. Okay, so gentlemen, that's the introduction to the types of reactions and predicting products. So you should be able to know the 5 types of reactions, and given a set of reactants, determine what the products will be. That's what you'll be doing for your worksheet, and the worksheet is due tomorrow, Tuesday the 24th at 6:30 p.m. There's a link to turn it in. You can upload it. You can either print out the worksheet or do it on loose leaf. If you do it on loose leaf, the only thing is please be sure to be clear about labeling. So just have the title of the worksheet at the top and label each question clearly, so I know you did it. You'll just upload pictures of those or scans if you have a scanner, whatever you prefer. Or if you really want, you can do it in Google Docs, but it might be a pain to write chemical formulas in Google Docs. It's up to you, though. So get that turned in the 24th, and I'll have another activity or video tomorrow, Tuesday. So look forward to that. Have a good day, gentlemen.